Welcome to the Advanced Topics in Statistical Physics. This is Tasaki. In this mini course, I'd like to discuss a proof of the existence of a phase transition in the two-dimensional Ising model. I mean the most standard ferromagnetic Ising model. Okay, and when I say proof, I mean a fully rigorous mathematical proof. Okay, but I hope it's not too difficult, and I will give a complete proof. And this mini course will be self-contained. Okay. And in this part one, I like to discuss thermodynamics and phase transition in a uniaxial ferromagnet. So this is basically an introduction. And so let me start with thermodynamics. But don't worry, you don't have to care too much about thermodynamics. So I will just give it a brief description, and I think that's enough. But if you're interested in thermodynamics, one good textbook is mine, which will be published very soon from Oxford University Press. Okay. Now, the basic thermodynamic variables for ferromagnet, uniaxial ferromagnet, is T, the absolute temperature, H, the external magnetic field, and these two are intensive quantities, and N, the amount of substance, which is extensive. Okay, in this case, the free energy is a function of T, H, and N, and it's one of the complete thermodynamic functions of this system. Okay. And in some literature, actually including mine, this same function is denoted as G and identified as the Gibbs free energy. And in this case, it's related to F, the Helmholtz free energy by the Legendre transformation, and this M is the total magnetization. But anyway, you don't have to care too much about this. And anyway, we are interested in this F, free energy. And if you divide this free energy by n, the amount of substance, we get this free energy density, which is a function of only T and H. And from the general theory of thermodynamics, we see that this FTH is concave in H and satisfies this symmetry. Okay. And what do I mean by this? Well, concave function is a function which looks like this, and a rigorous definition of this. So gx is concave in x if this inequality is valid for any a and b and lambda. Okay, and this inequality means that if you pick these 2 points and consider this line, and also you compare it with this graph, part of graph gx, and then this part is always above this line. This is what this inequality says. And of course, it looks concave. Okay, so this is anyway the definition. Now, again, from general theory of phase thermodynamics, we see that the magnetization density is defined by this. So it's the minus of the derivative of F with respect to H. Okay. That was a general thing. And in a ferromagnetic system, we learned from experiment that there is a phase transition at a special temperature called the Curie temperature or the transition temperature, okay, which is denoted as Tc. Okay. Now, fix temperature to be above Tc and vary only magnetic field and measure this magnetization density. Then, of course, if you apply positive magnetic field, then this wants to be positive. If this is negative, this wants to be negative. Okay, and if H is very, very large, then it's this M sort of saturates. And if we decrease H to 0, then of course this also decreases and becomes 0. Okay, and correspondingly, the free energy density looks something like this, and it's differentiable everywhere. So in this case, no magnetization if no magnetic field, very natural. But if the temperature is fixed below Tc, something strange happens. So it's more or less the same here for very large H, but if we decrease H to 0 from above, then this M does not go to 0, but it remains at this finite non-zero positive value. And if you come from here, and then it stops here at a negative non-zero value. So mathematically speaking, this same function has these 2 different limits. If H approaches to 0 from above, then it goes to MST. And if it approaches 0 from below, it goes minus MST. Okay, so this MST is a positive quantity called spontaneous magnetization. Okay. Correspondingly, this free energy density shows a weird behavior. So here is a jump in this derivative. So, okay, you recall this m was a derivative of h. So since there was a jump in m, this means that f is not non-differentiable here. Okay. Physically speaking, this means that you have non-zero magnetization even at zero magnetic field. Very interesting. Okay. And this MST is a quantity that characterizes this phase transition, and it's called the spontaneous magnetization. And we define it in this way. Or you can define, this is more convenient and we use this. We can define the quantity called the right derivative. Well, this looks like the definition of usual derivative, but be careful. Usually here you have h going to zero limit, but here the limit is only half of this. So in this case, h approaches zero from above. Okay, and then this is denoted like this and called the right derivative. Okay, and so our MST is sort of can be defined in this limit, or it's equal to this. Okay, now you might worry about this equality and the existence of limits, and actually, but we can prove that this limit exists, and also this limit exists, and they are equal. Okay, and they are guaranteed by the concavity of f. And if you're interested, you can find it in the appendix of our book. Okay. Anyway, so this is just a definition of spontaneous magnetization, and in ferromagnetic system, this MST behaves like this. Above TC, it's zero. Below TC, it's non-zero and positive, and the graph looks like this. Okay, it's zero here, and it goes up, and it's like this. And here's the phase diagram at vanishing magnetic field. So here's TC. So everything is at h equals 0, and this is the temperature axis. And so below TC, you have ferromagnetic phase. Above TC, you have paramagnetic phase. Okay. And spontaneous magnetization MST is an order parameter that characterizes this ferromagnetic phase transition. Okay. This MST distinguishes between this phase and this phase. Okay, so these were all thermodynamics. Now let's consider, this is rather general consideration, but we want to discuss statistical mechanics, the relation between statistical mechanics and phase transition. Okay, we learned from experiment that this F, free energy density, is differentiable in H for temperature above TC, but it's non-differentiable in H at H equals 0 for temperature below TC. This is very weird. Can statistical mechanics describe singular behavior as this non-differentiability? So I don't want to go into detail, but roughly speaking, in thermodynamics, free energy density is written like this. Okay, and here this is energy, and this is sum over all states in all energy eigenstates. But anyway, in suitable model, this is a very simple function of h. Okay, and this is just a finite sum, like in Ising model. So if you sum up, and these are positive, sum up this very nice positive function of h, and take log, you get still a nice function of h. So this FTH can never be singular. I mean, it can never be non-differentiable. Wow. But as long as n, the number of spins, the amount of substance is finite. Okay. So in order to describe universal thermodynamic behavior, including phase transition, we need to consider thermodynamic limit, in which the system size, the number of spin, the amount of substance become infinite. Well, no magnetic material have infinite spins, but this is a kind of idealization we always consider in physics. Okay, so in order to study thermodynamic behavior, it is more convenient to consider very, very large system than, no. Okay, let me say this again. In order to study universal thermodynamic behavior, it is more convenient to study system in the infinite volume limit than treating finite but large system. Okay, so these are how F look like. These are rough pictures of how F look like for very large finite n and the limit where n is infinite. Of course, they are the same thing, and But anyway, if when n is very very large, then for low temperature F should look like this, and it's almost non-differentiable. But probably if you magnify this in a very drastic manner, then you start seeing that this is not actually not sharp, but you see you still have differentiability here. Okay, but if you magnify really, really, but in order to, I mean, studying such a case, I mean, function which looks almost like differentiable, not non-differential, but still differentiable, it is much easier, and it's much more straightforward to consider a function which is truly non-differentiable, and it captures what we observe experimentally or thermodynamically. So that is what we are going to do. So we will consider thermodynamic limits, which is one of the idealization, and try to justify this kind of behavior. Okay, that is well, this is one of the basic things that we want to prove in this mini course. Okay, so in order to do this, we study something usually called the Ising model, but it should better be called the Lentz-Ising model because Lentz is the person who proposed this thing. So of course, as you may know, this is an oversimplified model of uniaxial ferromagnets, and spin just takes two values up or down, and the interaction is very, very simple. Okay, so this is a very brief early history. In 1920, Professor Lentz proposed the model, and Professor Ising, Dr. Ising was his student, and Lentz gave this problem to Ising, and he solved it. This was his PhD thesis, and Ising solved it for one dimension and found no phase transition. And it seems like people believe that there are no phase transition in this kind of simple model. But there are something in between. I will come back to this. But in 1944, Lars Onsager, he is one of the giants. He's one of the gods in statistical physics. He has really important work in non-equilibrium statistical physics and everything. But anyway, this is one of his great work. In 1944, Onsager exactly solved the two-dimensional Ising model at zero magnetic field, and he found a phase transition. Okay, and this is also a very important topic, interesting topic, but we're not going to discuss this exact solution in this mini course. Okay, instead, we discuss something else. So as I said, there was something here. That is 1936, before Onsager, Professor Rudy Piles argued that the two-dimensional Ising model, or Ising model in higher dimensions, should have a phase transition. He found a very beautiful and essential argument suggesting the existence of phase transition. And then later in 1964-65, Professor Griffiths and Professor Dobrushin, he is basically mathematician, and Griffiths is a mathematical physicist. They provided a fully rigorous proof of the existence of a phase transition in the two-dimensional Ising model and higher dimensional Ising model by sort of improve by making a rigorous version of Piles' argument. Okay, so this is Professor Piles, and this is Professor Dobrushin. And well, actually, he's not related to this story, but this is Professor Harry Kasten. He's a very famous probabilist, and he works on percolation and things like that. And I like this picture very much because actually I have met and talked to these three great scientists. So it's here. And actually, I have never met Professor Griffiths. Okay, but anyway, and this is the topic of this mini course. Okay, and we're going to discuss this proof in part 5 of this mini course. Okay, and of course, this is just a very brief early history of Ising model, and there are many, many, many beautiful works related to Ising model, many beautiful, important works related to Ising model, and that continues to today. Okay, but there's no time for speaking about this. And you might say, well, but isn't this a very, very simple, oversimplified model? And it's a kind of toy model. So why do you care about such a toy model? But I would like to stress that this is not a toy model. It's a very important model that allows us to study universal aspects of physical system with many mutually interacting degrees of freedom. Okay. Um, Actually, this is my favorite topic, and I can discuss this forever. If you want to read extensive discussion, please look at my book. This is about, as you see, quantum many-body system, and it has a beautiful illustration by Mario Kazaki, very famous manga artist, Japanese manga artist. But anyway, this is my book. And in this introduction of my book, I discuss this kind of thing. And of course, in order to read this, you have to go to library or you have to buy this. But you can read this part, introductory part, for free. So it's on my website. So I will put a link to the comment of this YouTube video. But briefly speaking, let me say a brief thing. So we are interested in sort of something we call universality class. Describing some very interesting physical phenomena. And within this universality class, we have some system which are very, very complicated and which has many, many details. But we also have some idealized models like the Ising model, which is easier to treat. But I stress that these idealized models like the Ising model are not simply made up. They are not easy game. They are not simply a toys. They are non-trivial systems that capture only the essence of the phenomena that we wish to understand. So Ising model is not easy to understand. And if we understand Ising model, we understand something more than Ising model. We also understand something very essential, something very universal about phase transition and critical phenomena associated with the breakdown of GT symmetry. Okay, but anyway, I cannot spend all my time for this. So please, if you're interested, please look at my book. Okay, so this is the final slide for this part one. So this was part one, introduction. In part two, I'm going to define the model carefully, and I will discuss the main theorems. And in part three, this is very important. I prove the existence of infinite volume limit of the free energy density. And then we show that it is differentiable at H equals 0 for high temperatures. And we also show in final part that this F is non-differentiable in H at H equals 0 for sufficiently low temperature. Okay, so I hope you will come back and I enjoy these parts.